Hi, and welcome to our discussion on mountain wave. We talked about all of the certain different types of flows that can develop in the mountains. We talked about thermally driven flows and also block flow and flow that follows the terrain. Now we're going to discuss when a wave develops in the mountains. And the wave that develops, the type of wave that develops, depends upon a number of factors. It depends upon the environmental temperature profile. In other words, is the atmosphere stable or not stable? And also it depends upon how the wind changes with height, or the vertical wind profile. And also other factors such as the size of the mountain and how it drops off downwind on the lee side of the mountain. So there are two types of waves that can develop. One is called the vertically propagating wave. The other one is the trapped lee wave. In this video, we're going to discuss vertically propagating waves. And vertically propagating waves are waves, gravity waves. We talked about gravity waves. So these are gravity waves whose energy actually propagates vertically, goes up with height and increases strength with height. So the requirements for a vertically propagating wave is weak wind shear, so wind does not change much with height, and also a moderately stable atmosphere. And this is assuming that the winds are blowing perpendicular to the mountain range. In other words, winds are blowing over the mountain, and the FAA states that a good threshold wind speed at mountaintop is 20 knots. If you see 20 knots of wind, then you should start thinking about mountain wave activity. And specifically, we're talking about vertically propagating wave. So with a vertically propagating wave, the wave is much stronger or higher amplitude at higher altitudes than it is at lower altitudes. And in this diagram or this picture, you can see that the wave doesn't have much amplitude right above the mountain, but as you go higher through the atmosphere, in particular maybe about 5, 6, or 7 kilometers up, which is about 18 to maybe 20, 25,000 feet, you notice that the wave has a much higher amplitude. Another thing also is that the wave actually tilts backwards or upwind with height. So that down low, what the red line indicates here is the trough in the wave, and you can see how the trough in the wave extends back over the mountain with altitude. And as I mentioned, the amplitude increases with height. Now with a vertically propagating wave, typically you only get one cycle of the wave, perhaps two, but it's not a wave that extends very far downwind. You may have heard mountain wave in your other classes. They talk about how it extends hundreds of miles downwind. This is not one of those. This one only extends typically tens of miles downwind, and we're talking maybe 20, 30 miles or so downwind of the crest of the mountain. So it's very close to the mountain, right over the mountain. And the hazards with vertically propagating waves are typically felt in the mid to high levels of the atmosphere, high altitudes. So we're talking altitudes of anywhere from maybe 20 up to 60,000 feet. Aircraft flying above the mountains at high altitudes have reported mountain wave activity in excess of 60,000 feet. Now, this wave is not necessarily bad if the wave is laminar flow. In other words, if it does not break, if there's not turbulence with it, then of course you get a smooth ride, except that you're going up and down. You have updrafts and downdrafts. But the worst case scenario is that the amplitude of the wave becomes so great that the wave breaks. And when you have breaking wave, it produces severe to extreme turbulence. This is typically concentrated to anywhere from about 20 to 39,000 feet. And of course, near the tropopause is where you usually have the worst type of turbulence. Here's an example from back in 1972 research project where they were flying wave with several aircraft. And this is a vertically propagating wave that they experienced at high altitude. You're looking at 200 millibars. Up at 200 millibars, you still have wave, and 200 millibars is approximately 40,000 feet, 39 or 40,000 feet. You can also see that they had wave activity down low, and that was a hydraulic jump, and we'll talk more about hydraulic jump and strong downsloping winds later on. But you can see the wave here. The wave has a wavelength of probably about maybe 10 or 20 kilometers. So in other words, or the nautical miles. So you can see that this is not a very big wave. It happens very close to the mountain, not very far downwind of the mountain. Typically if it breaks, you've got a lot of turbulence. So most of your problems are at high altitude, but you can have also low altitude problems with a vertically propagating wave if you have strong downsloping winds and hydraulic jump, and we'll talk about that later. So when you're flight planning, what do you look for vertically propagating waves? Well, number one, you got to have some component of the wind that's blowing perpendicular to the ridge line. And as we said, kind of a threshold wind speed is 20 knots according to the FAA. 20 knots at the mountaintop, winds blowing across the mountains. And then look at the winds at the mountaintop or at the ridge level, and then 6,000 feet above the ridge level. In this example, we're looking at the winds at 12,000 feet, that's the top of the mountain, and then another 6,000 feet above that would be 18,000 feet. So we've got at 18,000 feet winds that are 70 knots, at 12,000 feet, 50 knots. Take the ratio of those two, in this case 70 divided by 50, and if that number is less than 1.6, then you are going to more than likely have a vertically propagating wave. So other ways that you can look for vertically propagating waves, if you see high altitude turbulence or high altitude wave activity. So in other words, you can look at Airmid Sigma, center weather advisories, meteorological impact statements. In this example, the Sigma is telling you that there's turbulence up high. High altitude turbulence is an indication of vertically propagating waves, one indication of vertically propagating waves. Also, pilot reports, if aircraft are reporting strong updrafts and downdrafts high in the atmosphere, as you see in these examples, are reporting severe turbulence up at 31 or 41,000 feet, then you know that you've got vertically propagating wave. Also, there's a pilot report indicating turbulence down low also, and that may be an indication of other things going on down there. Also, the METARs typically indicate the presence of a vertically propagating wave when you look at pressure jumps. If you see pressure rising rapidly or falling rapidly in the remarks section, if you see rotors, a lot of times those are also indications of vertically propagating waves. You can also see those rotors with other waves too, and we'll talk about that later on. But also strong winds, gusty winds at the surface. When you have strong downsloping winds also sometimes happen with vertically propagating waves. But one of the best ways to identify a vertically propagating wave is using its satellite, looking at satellite. And looking at Colorado, which is right smack in the middle of the satellite image, you can see just a cloud mass. But if you parse the satellite imagery a little bit more carefully, you can see that there's a little gap or slot in the clouds. And that clear slot usually is a good indication of a vertically propagating wave. The reason for that is as the air ascends over the mountain, it condenses and produces a cloud, which is called a phone or cap cloud. As the air descends, it will evaporate the cloud, so you have this clear area. And then in the other part of the wave, as it jumps back up, you'll get clouds. So that's an excellent way of identifying the vertically propagating wave. So we're done with vertically propagating waves. In the next video, we are going to discuss trapped lee waves.